Welcome to Drone System and Control course, lecture 4. It talks about rigid body transformations. In the previous lecture, we discussed about what is rigid body, how do we do the coordinate transformation from one frame to another frame. We also discussed about inertial frame, which is a global reference frame, local frame or body frame, what we call as a local frame, and we discussed about how do we do transformation from local frame to inertial frame and inertial frame back to local frame. In this particular lecture, we will talk about need for such transformations in terms of navigation and control of these drones. Rigid body transformations includes translation and rotations. We will talk about how its translation and rotations are taken place here, and we will also introduce degree of freedom. Let us do a little recap on vectors and coordinates. Any point P, if it is two-dimensional plane, if you are looking at, for example, the drone is kept altitude constant and navigating in only in xy plane, then we just represent the whole equations of motions in 2 degree of freedom. So, then any point in that frame is represented as Px and Py. I am just depicting here how this Px, Py represented in xy plane, and origin is O. Here is a frame of reference that what we are taking for navigation, right. It could be a global frame of reference. Sometimes we may have to navigate the drone in a 3-dimensional plane, then any point P can be represented in a Px, Py, Pz, right. So, we can just talk about navigation in 3-dimensional plane x, y and z. Here we use global frame of reference, and origin is the center, right. So, linear transformation is the one that is represented by simple matrix operations. Y transformed, x is transformed into y by a linear transformation A, right, where x is r power m in general dimensions I am talking about, and y is also an r power m, A is a m cross m matrix. For example, in 2D plane, this operator takes a form qx and qy or the new point, transformed point from Px and Py, then the A matrix is 2 cross 2 with the elements being A, B, C, D, then Qx is Apx plus Bpy, and Qy is Cpx and Dpy. Suppose if you are doing 3-dimensional plane, the linear transformation takes from Qx, Qy, Qz is a new point from Px, Py, Pz, A11, this matrix transformation matrix is a 3-dimensional matrix 3 cross 3 with A11, A12, A13 likewise all the way to A31, A32, A33, right. So, we can do the linear translation from point 1 to point 2. Here x to y. Rotation is also a linear transformation, y translation is an affine transformation. Right. Now, look at the translation in 2D just for an understanding. Translation refers to movement of a rigid body without any rotation. Pure translation, there is no change in shape or change in orientation. In our case, there is no change in orientation, right. What I meant is I am moving a point O to O prime, that is a new position, and I am trying to look at the change from x volt to x nu, y volt to y nu. The Tx is the distance travelled in x direction, and Ty is the distance travelled in y direction space, right. Every point moves same distance in same direction, right. That is a very important, we need to look at in translation in 2D. Orientation of the body does not change. The rigid body orientation remains constant in O as well as in O prime. If you look at a rigid body, as mentioned earlier, it has a lot of points, right. All those points move same distance and they follow a parallel path, right. For example, if I am looking at a rigid body which is translating from a point O to O prime, any point I just take here, they will move a same distance, they will have a parallel path, because the orientation of this rigid body does not change. All body will have a same velocity and same acceleration in the motion. Translation motions are generally governed by Newton's second law of motion. Right. So, the distance d travelled by this is square root of Tx square plus Ty square. Tx is the displacement in x dimensional space, Ty is the displacement in y dimensional space. Right. That is the d which travels in from O to O prime. Now, rigid body translation. Right. What we know, all points move same distance in the same direction over a time. Unlike rotation, translation does not involve any angular motion. So, if I want to represent this in a mathematical form, the position of the rigid body undergoing a translation motion will be given by P of t, it is at time t is P naught plus d of t. D of t is the distance at time t, right, from the position P naught. Displacement is always a vector over a time because we are just looking at dynamics of the system, right, and we are going to derive the dynamics of the drone and we are going to analyze his performance. So, we are representing this in this form, right. This is an affine transformation. What are the characteristics of rigid body translation? If you look at no change in orientation, very important, you just have to look at it, right. There is no change in orientation of the vehicle when they go translation motion. The object remains aligned in the same direction throughout the motion, that is very important. Parallel motion of points, every point on the rigid body moves identically, right, which means all of them moves parallel, right. Defined, if you want to define by a single vector, translation is described using displacement vector d, right. So, any position p is P naught plus d. Okay. There are different type of translation. Okay. So, there is a rectilinear translation, curvilinear translation. What is rectilinear translation? Motion occurs along a straight line, right. Velocity and accelerations are constant in magnitude and direction. For example, drone moving forward in straight line without rotating. Think about it, drone take off from the ground and go to a particular height. Now, it is in the hover position. Now, I am going to move forward with height being constant, right. That is a rectilinear translation motion in xy plane, right, because height being constant. Curvilinear translation, motion follows a curved path. For example, here you see motion follows a curved path. This is a rectilinear transformation example, right. The velocity and direction, velocity direction changes, but no rotation occurs. What I meant is this particular rigid body remains in orientation same, only the direction of the velocity will change. Okay. Drone following a parabolic trajectory while descending, if this is a typical example for a curvilinear translation, right. Now, let us look at another important aspect, rotation. What is rotation? Rotation refers to the motion of a rigid body around a fixed point, usually at the center of the mass, okay, at CG point, right. Rotation of the body changes, but it does not change the shape or size because it is a rigid body, right. Unlike translation, in rotation different points move along different circular path. Okay. Rotation affects the orientation of the vehicle, but not the position of the vehicle, right. It is governed by Euler equation and rotation kinematics. We will discuss this a little later in the course. Okay. The center of attitude control, basically if you wanted to change the attitude of the drone, right, I wanted to change the where it is looking, orientation of the vehicle, where the pose of the drone, if I wanted to change, I need to rotate the drone to a specific location, right. So, that attitude control system governed by the rotation. Okay. Orientation, basically this is very important because orientation is also determined the heading or direction in which the drone is going to fly, right. So, we usually represent this as in either using Euler angles or using quaternions, or we represent it using rotation matrices. Now, let us understand rotation in 2D frame. Okay. Let us look at, if you see the A, right, let us point P is the drone is at the point P and x, y represent the frame of reference. Okay. Now the frame of reference is rotated by angle theta, right. The position will P becomes P prime in the rotated frame of reference, x prime and y prime, right. So I am just representing here, you can just see this is P prime, and the distance with respect to x and y axis remains constant, Px and Py. Okay. Now P prime I wanted to represent with respect to the original axis x and y, right. Now let us see what I am talking of. If I take with respect to original frame of reference xy, the P prime located at Px prime, which is on the negative x axis, and Py prime is on the positive y axis. Okay. Now I am trying to resolve, right. If I am looking at vector along this path, right, I am just talking about this is a unity, I am assuming the distance is unity, then I am talking of this y is sin theta and x axis will become cos theta. If I am trying to represent x prime along this direction will be a vector cos and cosine and sine, right. The same way, if I am just looking at a vector along the y prime axis, y prime will have negative minus sin theta and cos theta. And if I am just translating this, right, a point P to P prime, I am trying to represent this particular point, then this Px will become Px cos theta and Px sin theta, and the y will become minus Py sin theta and Py cos theta. So if I am just doing a 2D rotation, r theta is cos minus sin, sin cosine. This is the rotation. So any point in original xy can be transformed to P prime easily using this. Okay. Just I am simply applying the parallelogram rule to derive the rotation matrix for 2D. Okay. So let us look at Euler angle representation. In our course we will be using Euler angle representation for representing the dynamics of the vehicle. Okay. Now what I am trying to say, phi is the roll angle, rotation about x axis. If you look at this, it is a rotation about x axis. This is my roll, right. Theta is the pitch, right. It is rotation about y axis. This is a y axis. This rotation is my pitch, right. Sign convention need to be fixed when we are deriving the dynamics of this system. So we need to do what is clockwise rotation. That representation is very important, right. Psi is a yaw, rotation about z axis. So I am rotating about z axis. So ux, uy, uz are representing the direction of x, y, z, right. So we talked about coordinate frame of references, right. So you remember that and you can connect and see the angles, Euler angles are representing rotation about those x, y, z axes, right. So we are representing in 3D rotation of a rigid body. We usually represent any pose of the drone by using a 3 sequential rotation about different axes, right. This is used for deriving dynamics, not just only for drones, robotics, and it is also used for used in computer graphics to track orientation, right. So if I do a 3D rotation, yaw rotation if you look at, I want to find out Rz is rotation about z axis, and what is the angle is a psi. If I am trying to derive, right, it is cosine minus sine, because if you see only the x and y undergo change where z remains constant. So that rho 0 0 and 1 and 0 0, that doesn't, z doesn't affect, right. Now if I look at a pitch rotation, that is theta about y axis, you see the second row 0 1 0, rest of the terms will have the angle of rotation comes into picture. Roll rotation is about x axis, rx phi is the x axis remains same, that is 1 0 0, cosine minus sine, sine cosine, right. Now if I want to look at any of the rotation, I can do a sequential, first rotate in x plane, rotate in y plane, rotate in z plane to orient with respect to the new orientation of the vehicle. Then I can get the rotation matrix R is Rz, Ry and Rx corresponding angles of Euler angles of rotation psi, theta and phi. Now, let us get more details or understanding on the rigid body rotation. All points on the rigid body move in a circular path, as I mentioned earlier, around a fixed axis. The changes in the orientation of the body without altering its shape or size, because we are looking at a rigid body here. What are the characteristics of rigid body rotation? Fixed axis of rotation, all points move around the common axis, different velocity at different points. Points further from x axis move faster, whereas point closer to the x axis will move slower. Just to give an example, described by angular quantity, this uses angle, angular velocity and angular acceleration will come into picture to represent the rigid body rotation. Right. Mathematically, if I want to represent, rotation is characterized by Euler angles phi, theta, psi, and the rotation matrix R theta. From theta is the rotation angle. I am just giving an example. Here rotation about z axis, right. This is the matrix R theta, right. If I am trying to do full 3D motion, rotation about all axis comes into picture. I move one at a time in a sequential fashion, Rz, Ry, Rx. The product of all three rotation matrix will give me R, which moves the orientation from original orientation to the current orientation, right. If you look at the types of rigid body rotation, there are two types. One is rotation about a fixed axis. The body rotates about around the stationary axis. Every point here follows a circular trajectory. Example here, for example, drone yawing, right. You hover the drone about a z axis, drone starts rotating, that is a yaw. It can be rotate left or rotate right, right. Rotation about a moving axis. Axis of rotation itself moves, occurs in a complex motion like a UAV maneuver. If you are trying to do obstacle avoidance, right, obstacles you wanted to avoid and go on the motion. So, your rotation axis itself moves, right, that is what I just mentioned. Here quadcopter, suppose there is an obstacle in your forward path, you have to move, right. Quadcopter have to move forward as well as roll about the axis to avoid the obstacle. Let us look at how this is relevant to rigid body concepts in drone, right. So, if you look at the x axis y z, you have a translation motion, you have a rotation motion. Translation we call surge, sway and heave, if roll, pitch and yaw in the rotation, right. Drones are treated as a rigid body, right. We ignore the deformation, ignore some bending might happen because of the thrust and effect. We ignore small deformation which is negligible, right. The degree of freedom for the drone is nothing but number of independent parameters required to describe the motion completely, right. In our case we need 3 translation and 3 rotation, and hence the degree of freedom is equal to 6 here, 3 for position and 3 for orientation, right. We make some assumptions when you are doing this representation. We build, what we do is we need this to build an algorithm, control algorithms. We need to find out what control law we can develop such that the rigid body follows the trajectory of our interest, right. We also need to fuse the sensor data, measurement data to fuse to get the state estimation. We will be studying about it in the next lecture. We also look at simulation of the flight. See, once the drones are built, we need to create in a simulation world where we have to mimic the actual performance of the drone in a simulated world. So, we can understand the performance of the drone under different conditions. Suppose if there is a gust, what will happen? How much of endurance will decrease? All that study can be done if you have a perfect model. We will study about modeling and simulation in the next lecture, where you will be able to appreciate why this is required, right. And this model is also required for us to develop the control law, so that the desired trajectory can be followed by the drone and achieve the mission completely. So, we will study all this in the next lectures, right. Now, in a summary, what we covered in this particular lecture we talked about rigid body rotation and translation in 2D and rigid body rotation and translation in 3D, Euler angle rotation and of the rigid bodies, and we looked at the in the previous lecture we talked about how do we do the transformation from inertial to body frame to inertial frame. Before completing this lecture, I just want to take you through a small MATLAB demonstration how we do the transformation. Okay. So, just looking at coordinate transformation in rotation matrix, it is very easy to get this transformation in rotation. It is not only required for drone, it is also used in robotics, whether you are using ground robot or you are doing a manipulator, you need the coordinate system and transformation matrices. Okay. One can easily apply this principles. If you see here, example I am just taking, it is a 3 degree of freedom model I am taking. It is a fixed joint and a revolute torso joint connected to the base. The second joint is revolute and the shoulder joints are shown here. So, just to give you an understanding for you, theta 2 is the rotation about z axis and for z2 it is theta 3, right. So, we are just trying to see how we can represent, right. So, for example, when I mentioned in a lecture vector transformation, so here I am representing R, right, it is a point, right, and it is a 3 cross 3 rotation it take place. The translation happening is 3 cross 1. So, how do we represent this particular point and how this point moves in a 3-dimensional plane, we can understand better. For example, P here, if you see P is a vector, right, P is a point and a 3-dimensional plane. I am representing as 3 cross 1 vector, 3, 4, 5, this is a vector, right, which represent what is the displacement of the point from the origin with respect to x, y, z axis, right. We also would like to define the coordinate system, right. Here how the coordinate system is there. So, I am representing the coordinate system to be 1, 2, 1, my body where it is present. So, I am just representing O1 is my coordinate system where the origin is represented by that. Okay. Now, how you will calculate the distance between these two, you can just do a simple subtraction between the point P and O1, you will be able to get, right. So, just to give a notional representation, here you see at the bottom I am talking about x naught, y naught, z naught being a 3-dimensional representation, and if I am doing a rotation then it will become xt, yt and zt. So, how do we move from P1 because of the rotation to P naught, right. P naught equal to R1 naught P1. See, rotation from R1 to R0, that is a rotation matrix, right. The point P is measured with respect to the frame 0 and frame 1, right. These two operations are having a translation and rotation are combined in the following way. P1 is R01 P naught, right. We know P is 2, 3, 4, let us say. Rotation, what we are doing, we can just control the angle, how much angle you wanted to rotate. Let us say I wanted to do a 5 degree rotation. If you see I have a sliding bar, I can represent what is the angle of rotation in x axis, angle of rotation in y axis, angle of rotation in z axis, I can set this. Then you have x, see as I mentioned earlier, whenever we calculate the rotation matrix, we do it in a sequential fashion. We rotate in x axis, rotate in y axis, rotate in z axis, all three combined together we will get a rotation matrix. If you see here Rx, right, Rx is 1, 0, 0, is rotation about x axis, Ry is rotation about y axis, that is why the second row of the matrix is 0, 1, 0, Rz is a rotation about z axis, right. It is the third row is 0, 0, 1, I am using that, and I am trying to get Rxy, which is a combined rotation due to x, y and z. That is my combined rotation, right. Using the combined rotation, I can now, once I have the rotation matrix, I can move any point P to new point P1 straight away, right. Now, if you want, if you use R, Y, X, Z, then you will get the current point P2, right. So, you can get this, right. So, Again, if you add the translation element to it along with the rotation matrix 3 cross 3, in this case, because it is a fixed joint, translation in one dimensional space, you had another one row to it. Okay. So, once you combine everything, you can just do the rotation and translation in simultaneous fashion. This particular MATLAB file will be uploaded in our notes folder. You can download, you can try, so that you will get an understanding of any translation and any rotation, how you can do, how you can represent in MATLAB and simulate, right. This is very important, because when we move on to dynamics of drone, we need to understand how we can convert or how the measurement taken from body frame to inertial frame, right, by knowing Euler angles. So, you will get an idea how to do this in MATLAB. Thank you so much.